Hello friends, welcome to my channel. Today we will going to talk about the enamine chemistry. Okay, so first we will talk about the formation of enamine and the reaction conditions. After that we will talk about the regio-selectivity for the enamine formation, and after that we will talk about Stork Enamine Synthesis and how enamine acts as a substitute for a enolate and how enamines are alkylated, and regio-selectivity about the alkylation. We will discuss about that. So let's start. So enamines are formed from the reactions of carbonyl and secondary amine, and those carbonyl will react to give enamine, which carbonyl have at least one alpha hydrogen at one of its side. This is the reaction course for the enamine formation. So at the first step, the secondary amine, the lone pair of the nitrogen, nucleophilic attacks at the carbonyl center, forming a tetrahedral intermediate, and after that a dehydration occurs of the intermediate. You have to remember that every step of enamine formation is a reversible one. Okay, so if you take a close look on the reaction scheme of the enamine formation, for the dehydration step you will observe that the acidic condition will favor the dehydration process, because if in the reaction medium there is enough amount of H plus, that will convert OH group into better living group water, and that will help to eliminate the OH group and forms the enamine. But you have to remember that there is a secondary amine, so if you increase the acidity or decrease the pH of the reaction medium, then the secondary amine can be protonated, and if the secondary amine is protonated, so the secondary amine cannot react as a nucleophile. So you have to keep both things in your mind. So because of this fact, we have to maintain an optimum pH which will satisfy both this step very much, so that the reaction can be carried out, and the optimum pH is slightly acidic. You have to also keep in mind that if you take another look at the reaction course of this enamine formation, the water is being generated at the end of the enamine formation. So as both the step of the enamine formation is reversible, so to drive the reaction to the right side to get the enamine, we have to continuously keep the water molecule out from the reaction medium, so that to drive the reaction to the right side. So this is the important aspect for the formation of enamine. Now we will talk about the regio-selectivity of the enamine formation. So we have taken an unsymmetrical ketone, cyclic ketone, and a secondary amine we have taken as a condition for the necessary condition for the enamine formation. TSOH acts as a proton donor. So as this unsymmetrical ketone have two types of alpha proton, so there is a possible chance of getting two types of regio-isomer of enamine. So let's just write both the enamines one by one. So we got A and B, two enamine from the elimination of two types of alpha hydrogen from the unsymmetrical ketone. So by take a close look, you will conclude that the enamine A will be the major product. The A enamine have the more substrate double bond, but this is not the actual case. The enamine B is the major product. So we will explain how B is the major product for this enamine. So I am just writing both the stereochemical structure of both the enamines one by one. So I have just written a stereochemical structure of both the enamine, and now we will all agree to that fact the enamine have a 2 resonance structure. So this is the resonating structure of the enamine. Actual structure of the enamine will be hybrid of these 2 resonating structure. So to carry out this type of conjugation, the N and 2 carbon of the carbonyl have to be kept in a same plane to carry out this type of conjugation. Otherwise the lone pair cannot be conjugated with the CC double bond. Okay, so these 3 atoms has to be in a same plane to carry out this conjugation, and obviously that happens in the enamine, that these for both the possible enamines in C and C has to be a same plane to be present in a conjugation. So if these 3 atoms are in a same plane, so let's take a look for the enamine A. What is the condition here? So if these 3 atoms are in a same plane, then this attached CH3, this C have a sp3 hybridized, so the all hydrogens are specially distributed, 109 degree angle almost, and here is also a sp3 carbon which also have 2 hydrogens. So these hydrogens from these 2 carbons are very close to each other. Okay, so they experience a severe repulsion to each other and steric hindrance among themselves. But such case, if the enamine double bond CC double bond formed at this side, so here is also only a hydrogen is there, so that will not experience any steric hindrance with these hydrogens of carbon. And if we consider at this stage, this carbon is neither in sp2 hybridization, this is sp3, so this bond is not in the same plane of this carbon. So for the bond orientation is very much than that of the sp2 center, so that can specially arrange themselves to minimize the steric repulsion with these hydrogens. There could be some interactions, but that will be much less than repulsion than this phenomena, because here this bond has to be a same plane, so that will interact with this carbon's hydrogen. Okay, but here it is not a sp2, this is sp3, so the bond can rotate itself to minimize the repulsion, but here it is cannot be possible just to maintain this conjugation. Okay, so due to this fact, the regio-selectivity of formation of less substrate double bond will be predominant, so we'll get enamine B as a major product. So all the reaction will be carried out upon this less substrate enamine, which is the B enamine. So as we observe the resonating structure, I am again rewriting. So this is a resonating structure of the enamines in general. So what you can observe is that the enamine can act as a ambident nucleophile. This nitrogen has a lone pair which can also act as a nucleophile. Or again, in another resonating structure, this carbon has a negative charge upon it, so it can also act as a nucleophile. So this enamine acts as a ambident nucleophile. This is a C double bond C. So if this lone pair comes here, this gets the negative charge. Carbon has some nucleophilicity in it, and nitrogen also has some nucleophilicity. But as the nitrogen is more electronegative than the carbon, so nitrogen center is more, both the nitrogen carbon center are soft, but the carbon center is much more softer than the nitrogen center. So any interactions with the any soft such electrophile, the carbon center will give a major product. Nitrogen center also gives some amount of product through that nucleophilic center, but carbon center will be predominant. So from the 2 resonating structure of enamines, it is evident that the enamines can act as an ambident nucleophile. So in 1954, Gilbert Stork of Columbia University showed to us how enamine could be an alternative of enolates, and enamine can also be used for alkylation or acylation of aldehydes and ketones. So since then, enamine have been extensively studied and used in organic synthesis. And now we will discuss the use of enamine for the alkylation and acylation to the aldehydes and ketones. So enamine synthesis, and we have already discussed, is named as the Stork Enamine Synthesis after the name of the famous Gilbert Stork. So this is our next reaction when a 5-membered ketone is reacted with 6-membered secondary amine, and here we can first expect the enamine formation, which is a pretty straightforward. So let's write the enamine. As I previously discussed, the which center acts as a more good nucleophile. So if I give a alkylating agent which is a methyl iodide, reacts very fast in dioxane medium, so which center will be alkylated? You can say that the nitrogen lone pair can alkylate this carbon, and also there could be this type of reactions can also occur. From this double bond goes to CH3 and I minus cleaves, so both type of product can be formed. I am writing both the products. So if alkylation, C-Alkylation occurs, then we get this product. As corresponding I minus, which cleaved as a counter anion. This is a C-Alkylation, and if the N center attacks this carbon center, then we get I minus is the corresponding anion. So this is the N-Alkylation product, and the experimental data suggests that the C-Alkylation product is formed at the 65%, and the N-Alkylation product has been formed in 35% yield. So what you can get from here, that as the carbon center, which is a soft center, so that will favors the soft interaction with this incoming alkylating agent, because there is a delta plus charge at the carbon center. So that will carry out a soft interactions. The C-Alkylation product is the major product, which is 65%, and N-Alkylation product, N is also a soft center but less softer than the carbon center, so that is also give a significant amount, which is 35% of yield. Okay, but there is an interesting fact that if we heat this mixture prolonged time in same dioxane medium, we get a little bit change in percentage of product. We get C-Alkylated, the same product, in 95% and N-Alkylated product in 5%. If we reflux this reaction mixture in dioxane in the same reaction medium for very long time, so you can only conclude one thing, that C-Alkylation product is our thermodynamically controlled product, that is the TCP, and the N-Alkylation product is the KCP. That is because if we give the reaction to carry out for a long time, then the actual more stable or the more thermodynamically stable compound will be predominant at 95% yield, and the N-Alkylated product is only 5% yield. So this data suggests that the TCP thermodynamically C-Alkylation product is the thermodynamically controlled product in the enamine alkylation of the enamine. So in this connection, it is worthwhile mention that you can see that the enamines are very good, acts as a good nucleophile. So you can also compare the enamines with the enolates also, because enolates also have a similar structure, thus just change of the nitrogen, there is oxygen. Okay, but their oxygen have a negative charge, so the reactivity of enolate is higher than the enamine. Okay, but the types of reaction is almost similar. So like the enolates, the enamines also reacts with alpha beta unsaturated carbonyls and alpha halocarbonyls, also the similar type of reactions. So next we'll talk about some reactions involving enamine formation, which you get some interesting observations in the products. Let's discuss those examples one by one. From this reaction, there is an unsaturated carbonyl again has been given to you. So what we expect that from this compound? So obviously the less substrate enolate will be formed, and statistically also the these alpha hydrogens are in 3 and there is only one alpha hydrogen, and also that will generate a severe strain with this 5-membered carbon hydrogen in later stage. So we know that in exclusively this will give this enamine. So next question is a little bit stereochemical question. There is a stereochemistry involved in the enamine formation. So let's try that. So this is our next problem, where the amine, which is the secondary amine, which is a chiral one. Okay. So at first, in spite of chirality, the enamine formation won't have any effect. So it will get a normal enamine. Just write the enamine. So this is our expected enamine. After that, an alkylating agent is given, which is ethyl bromide in dioxane medium. So here is a fact that as I am writing this double bond in this direction, so if this lone pair gets here, so this will be nucleophilic site. So that basically attacks the carbon of the ethyl bromide. So it gets that and bromine leaves. But after the formation, what will be direction of the formed CC bond? The system will tend to minimize the repulsion among the reacting group. So there could be two possible products, because this center will be converted into sp3 center. So there is a chance of CC bond form at above the plane, below the plane. But if that carbon formed below the plane and this carbon is also below the plane, so that will experience a severe repulsion among themselves. So the major product will be those compounds where this carbon-carbon bond which will be formed will be above the plane. So nevertheless, let's just write both the enamines. These are the two possible enamines alkylation products after the alkylation of the enamine. Okay, so obviously this is a major product because here the two bulky groups are anti to each other. This is below the plane, this is above the plane, but here this is both the groups are in the same plane. So that will experience some amount of steric repulsion among themselves. So this will be the major product. So you people have always a question that what happens if the double bond forms at this side, because this is a symmetrical ketone. Okay, so double bond can be formed at this side, then this CC bond is above the plane, so the incoming group should be formed at the below the plane. So from that you will get this type of enamine if the double bond formed at this side. I am just writing that scenario here. So this is the case if the double bond formed at this side. So after that, what happens? If that reacts with the alkylating agent, which is ethyl bromide, for newly formed CC bond to here, which will be below the plane, just to minimize the repulsion with this CH3. So the major product from this you will get So after hydrolysis in acidic medium, from here you can get a product which is, because the C double bond end positively charged is always have a tendency to hydrolysis, so you get again the carbonyl group back, and there is a ethyl. And from here, as this is a major product, you can also have, after the hydrolysis, you get product which is this is above the plane. So if you take this compound and this compound, this is all is identical, because if you just rotate it, you will get this compound. So this is not enantiomer, okay, this is superimposable. So you can just place it on this. So this is superimposable, okay. So this is an identical product, this and this. So our next question is also about the acylation. So let's just discuss the problem. So you know that this just forms a enamine. So I am just writing the enamine. The reagents was given, which is a acyl chloride, which is RCOCl, and after with this there is a base given, which is in ET3, that is triethylamine. Okay, so what we can expect, this lone pair comes here, this goes here, attacks here, and Cl minus leaves. So we will get a alkylated product. But here is also a possibility of both the formation of N-Alkylation and C-Alkylation. So let's just write the both compounds, both the alkylations. So if I consider the C-Alkylation, we get So let's first discuss about the C-Alkylation aspects. Here you can see that this is a carbonyl and this is also equivalent to carbonyl, because this is C double bond N plus. Okay, so here is also a proton rather, which is doubly activated. So this is a very acidic one. Okay, so for that reason you can see that in the previous, during the alkylation, there no base has been used, but here a base is used, just because to capture this proton and give this kind of substrate. So this base just captures this proton, and this comes here, this goes here, so you get So why the external base has been used? Okay, this is just because of this hydrogen have a very severe acidity. So here is also a nitrogen in the enamine, which is also have a basicity of this nitrogen lone pair. So that lone pair just captures this as hydrogen and consumed and remains as a salt, which is a byproduct. I am just writing that here. So in that case, this NH plus the protonated enamine have no reactivity, because if the lone pair of the nitrogen is lost, then that cannot be acts as a nucleophile. Okay, so if the external base, which is more basic than this enamine nitrogen, if that the triethylamine is not used, enamine nitrogen will capture the proton. So that will consume excess enamine, and the enamine will lost its reactivity after the acylation. To suppress the enamine's activity towards this proton, the external base, which is more basic than this nitrogen center, so that just captures it and gives this kind of intermediate, and after that, if it is hydrolysis, it gives our desired acylated carbonyl, which is our product. This is the C-Acylation. So there is also a N-Acylation product, because you know that nitrogen center reacts with acylation, under acylation very fast and very with predominant. So there will be a N-Acylation, but there is a fact I will discuss, that if the, so I am just rewriting the enamine again. So if the N-Acylation occurs, what will be the product? So the product will be like this. So you have to remember that this reaction is a reversible one, but C-Alkylation, the C-Acylation is a irreversible one. So as this reaction is a irreversible one, in spite of forming a N-Acylation product, as this reaction is a irreversible one, this will keeps driving the reaction to the right side, to the C-Acylation side. So if the reaction moves to the N-Acylation side, it will reverse back to the enamine and drives through the C-Acylation side and gets this irreversibility, because C-Acylation is a irreversible one. Okay, so we cannot get a sufficient amount of N-Acylation product just because of this is a reversible reaction. So the next we will discuss a very interesting example regarding the enamine. So this is our reaction. So at first step, what is the product which is given a N-Alkylation product? So we can easily understand that the N-Alkylation will be the product. So let's just write the N-Alkylation product. So the nitrogen lone pair will attack this center, sees to bear, and bear cleaves. So you get this is an N-alkylated product. So after that, what happens, as this is a reflux in this acid in CH3N medium, so here what occurs that the 3,3 sigmatropic shift occurs. So this lone pair goes here, this comes here, and this forms a C double bond C. So what we get? We get a rearranged product. And there is a newly formed C double bond C. So after that, the hydrolysis takes place. We just hydrolyze the C double bond in. So we get our carbonyl back, but the carbonyl is now in the new position just because of the 3,3 sigmatropic shift. What happens that after we get abnormality in the product, then we try to explain the reaction course. So here what happens, the 3,3 sigmatropic shift. So for that rearrangement, the composition of the carbonyl has been changed. So this is a very important aspect. So this is all about the alkylation with respect to enamine. So if you have any problem, any query, just write in the comment box about the enamine. And I have already talked about the formation of enamine, condition, regio-selectivity of the alkylation, Stork Enamine Synthesis, how this carries out, the C-Alkylation versus N-Alkylation, everything I have discussed in detail. So if you have any query, let's just write in the comment box. Okay, so I am just providing some enamine based problems. So let's just practice it. Thank you.